Morning. So here is a question from 10.6. 10.6, we study equation of lines. Actually, we study equation of the planes. 10.5 is equation of lines. 10.6 is equation of the plane. So if we have two planes, then if the plane are parallel, which means they have the same normal vector, they will not intersect. But as long as they're coefficient, as you can see, the coefficient were 2, -3, 1, and -1, 2, -1. So they're not parallel, they're definitely intersecting. So two lines when they intersect, and two planes when they intersect, we got equation of a line. So determining equation of a line at the intersection of two planes is one of the topic in 10.6. So on the screen, we have a question to determine the direction of that line. So once we find out direction of line, it's not too hard to find the equation of the line. Let's practice that. I'll let you do the calculation and you're done. See if they are consistent. That's one of the chapter 10 question. So now that we're really officially reviewing, so you can see the question that we're doing are all over the place. It ranges throughout the entire textbook of chapter of calculus 2. So in calculus 2, we'll study the later few chapters, which is our chapter 10, 11, 12, 13, and 14. Chapter 10 focused on vectors. 10.1 was three-dimensional coordinate system, equation of surfaces. We studied a variety of surfaces. And then those equation of surfaces pop up again in chapter 12 and maybe also chapter 14. So 10.2 introduces the vectors and how to add vectors, subtract vector, or what's the meaning when vectors are subtracted or added, or how do we multiply a vector by a number. So 10.3 is dot product of vectors. 10.4 is cross product of vectors. With dot product of vectors, we also talk about how to calculate angle between two vectors. And with cross product calculation, we also talk about how to calculate area. With cross product, calculate volume. With cross product, 10.5 focus on equation of lines. Also, equation of line is a special kind of vector value function that we study in chapter 11. 10.6 is equation of planes. Also, equation of plane is a special surface, which we might occasionally talk about in chapter 14 and 13. So this one that we're working on is one of the examples from 10.6. Okay, I want to see how many of you already have the answer. Let me turn on the scanner. Thank you. So far, all the solutions are right. If you need a hint, you basically take out the normal vector and find their cross product. So essentially, bottom line, this is a cross product calculation. So you have the vector 2, -3, 1 from the first equation of a plane. The second plane, the vector is -1, 2, -1. And you find the cross product of these two vectors. That is a vector perpendicular to both planes, which will be right the cross product, but that will be the perpendicular to both of these two normal vectors. But normal vector of the plane is perpendicular to the plane, so So this line will be in both planes, so that it will be perpendicular to both vectors. That's the reason that cross product will help if we want to determine the direction of the line. This is normally the first thing we do when we determine the equation of the line at the intersection of two plane. It's a cross product calculation. You're getting an answer?
No, I just realized I was doing the wrong method, so.
It's the cross product calculation.
I,
Yes, you wasn't listening to me. You were doing
Sorry.
your own calculation.
sorry, I was trying to, I got so caught up in like trying.
Yeah, sometimes when you focus on something, you can barely hear anybody said anything. So we'll take out the normal vector for both lines. Let's call that N1, because the coefficient vector of the plane is a vector that's perpendicular to the plane. So vector 2, -3, and 1 will be a vector perpendicular to this plane. And the second vector is the normal vector for the second plane. That's -1, 2, and then -1. We are looking for a direction vector for the intersection, the line of intersection. It would be the normal vector. I should call that normal vector 1, normal vector 2. So we focus on the cross product calculation N1 and 1 cross N2. We've been doing cross product all the time now. Now that we're reviewing, so we cross multiply and subtract. It's 1 - 2. That was 1. Then we move the vector over. That would be 2, -1, and then that's -1. That's minus -2. So that's also 1. You see what we're going with this. And the last component will be this multiply, and then we subtract, cross multiply, subtract. Okay. So try to finish the cross product calculation. That's the directional. That's the directional vector we're looking for the equation of the line at the intersection of the two lines.
Oh, wait,
Okay.
sorry, I didn't.
Charles, you might want to double check because I saw that you have the wrong answer. You can see the first component, it was 1, 1, right? If I say that you find the answer that's not in. Okay. Okay, so check your answer, make sure they are the right one. I think the answer should be this one. Okay, if we finish the last calculation, cross multiply and subtract, it will also be 1. That's all three components are being calculated for the direction of the line. So that's the answer. So this is the kind of question that we had in 10.6. It doesn't take a long process, but it does have to have such an understanding of the relation between lines and planes. I think I got everybody's answer. Right. So that's our first practice question. I was trying to review what we were doing the whole semester. So chapter 10, we were going over content for chapter 10. The last section is 10.6, which is equation of planes. Now, when two planes are intersecting, we will have a line of intersection. To determine the equation of that line, we first have to know the direction. So here are that direction. Now, in chapter 11, we study vector value function. I try to indicate what was the variable correspondence. A vector value function, you have a one input variable and you have several output variables. The output variable are the coordinate of the vector, or the coordinate of the point we're going to So the output vector could be a two-dimensional vector, which give you a point on the XY plane. It could also be the output vector could also be a three-dimensional vector. That means given any input value, we're pointing to a single point in space. The content of chapter 11.1 is vector value function in general, introducing vector value function. 11.2 is being able to do calculus with vector value functions, such as derivative, integration, and so on, or in limit or limit continuity. So that's all 11.2. 11.3, we're using vector value function as a way to model motion. This could be something moving in a plane or something moving in space. This motion can be represented by two-dimensional function, two-dimensional vector value function, or three-dimensional vector value function. 11.4, we study unit tangent vector and unit normal vector. They were useful because they can be considered as component of the acceleration vector. So we find your vector value function, find its derivative, it's a velocity function. Find its second derivative, that will be the acceleration function. Acceleration function controls how where the object is moving. So the tangent vector is the direction when the object is moving, the normal vector is perpendicular to the normal vector. Acceleration vector is a linear combination of both. So every acceleration vector has component that's in the tangent vector direction and a component in the normal vector direction. 11.5, the topic is called arc length parameter and curvature. Now they each serve their own purposes. Arc length parameter is a special parameter, unlike the T we normally use. The S in the arc length parameter, when S go from 0 to 1 to 2, the distance traveled is exactly indicated by the parameter itself. So the parameter represent the arc length. That's why it's called arc length parameter. And then using arc length parameter, we can calculate curvature or lead out the notion of curvature. In the actual calculation of the curvature, we actually prefer to use whatever variable, whatever parameter we have. We don't have to be limited to the arc length parameter. So arc length parameter virtually lead out the curvature notion, but we don't have to follow it as a calculation of curvature. So for practice of 11.5, I was using this question. It's one of the questions that we had on what work. So the reason I pull out this question is one of those questions on the final exam. Yes, so it's question 11. I don't want to show it because I actually have the solution in there. So here we are. Let's pull out that question for practice. All right, we'll know the answer once we finish our own calculations. Work on these. I mean, it's not the first time we do arc length calculation, but there's always a little worry because people are not as confident with this than the first question. The first question is cross product and vectors, and a lot of people are pretty confident when it comes to vectors. We did really well on the first test, which means we had, in general, a good understanding of chapter 10. So when it comes to chapter 11, it's deviation. You are really, really confident on certain questions, not so confident on some of the questions. Arc lengths or calculating length of curve is one of the things I think is one of the things we need to practice more. Okay. Let me turn on the scanner. This is one of the questions that was on the homework. So if you did the homework, you might actually have notes. See how many of us still remember how to do it. Kind of like an extended version of the Pythagorean theorem. Thank you. If you haven't filled the course evaluation, please do so. Every semester, we send out email to students, try to encourage more people to fill out the course evaluation form. It's very important for us to improve our teaching, improve the course design. And you guys are the one that give us ideas or comment or give us suggestions. So please fill out the evaluation form. Also good for statistics standpoint. If there's any opinion that's only expressed by one or two students, it will be as persuasive. If we have a lot of students fill all the course evaluation, that made the data more convincing. So please try to fill out the course evaluation form. If you are even if you take only very short amount of time, provide only the multiple choice part of the form, because that one was easy, right? Just choose. The writing part it's your option. You can write more or write less or not write it at all. But the point is you have to do it. That at least we know that you did pay attention to the form. So I'm hoping that more of us are not skipping the evaluation process because you want to be part of the growing of the school. And you probably will convince some of your teacher to change the way we handle classes. Thank you. So far I see all the submitted answers are correct, so I suppose that this is not a super difficult integration. Some calculation. If you haven't really filled your answer, let me write the calculation. Right, length of the curve, we normally use L, which equal integration. We have individual integration limit. In this question, we have a vector value function that's parametric. So we integrate from 1 to 2. That's initial point, terminal point of the curve. And it's supposed to be root of the derivative of every component squared. So remember to differentiate. I still see people will square the whole thing. But you don't do that. You have to find the derivative of the vector first. So derivative vector of this vector value function will be 4t. And then 2 root 2. That was degree 1. Derivative of ln of t is 1 over t. So that's the derivative vector. Then we'll find the summation square of the derivative vectors, 16t squared. Square the first component, square the second component, we get 8. Square the last component, we'll have 1 over t squared. And this is a definite integral. Most people can actually find the answer now. But if not, let me analyze the process. We have a root calculation that we need to integrate. So one of the effort is try to figure out if this root can be canceled. So we look at what was inside. The root of 16t squared is 4t. So we have 4t plus the root of that term is 1 over t. So we have 1 over t and then square. You see that if you square this, you have 4t times 1 over t, which was 4. 4 times 2, that was 8. So this is equally exactly that part. So we have equivalent representation. So what you initially want to calculate is equal to this. Now the square will cancel the roots. This is essentially equal to 1 integrated 4t plus 1 over t dt. So that's really the integration after simplifying the square and roots. So antiderivative for 4t is 2t squared. Antiderivative of 1 over t is the natural log of t. We put it t equal to 2 and t equal to 1 for computation. So that we will have 2t squared is 8. 8 plus natural log of 2 minus, when the t equal to 1, we have 2 times 2. So that's everything. So we calculate in the end. And then that kind of goes with what you received. Question. E. So Jordan, you might want to double check. I see the answer should be this, right? 8 natural log of 2 minus 2. So if we simplify, it will simplify down to 6 plus natural log of 2. Amy, do you need more time? I see yours. I haven't submitted your answer yet. You there? The answer is supposed to be 6 plus natural log of 2. Right. If you need the link to the pleater, please let me know. But I saw that the line is lining up, so I assume you already have that page, and the page is already open. So I wonder what do actually answer question. Answer should be 6 plus natural log of 2. I'll wait a little bit. Right, so this is a practice question I selected out of the final exam practice question set. Here is a calculation of a curvature. We should be able to calculate the curvature for one-dimensional function, two-dimensional function, and then your one-dimension function, two-dimension vector value function. This is a third-dimensional vector value function. Being able to calculate curvature. That was one of also the practice question as well. Right. After chapter 11, we have chapter 12. Chapter 12 focuses on multivariable function, which means we have several input variable and have a output variable that we call fxy or fxyz, depending on whether the number variable is 2 or 3. So 12.2 introduce multivariable function. 12.2 talk about limit and continuity of a multivariable function. So there are a couple of tricky limit calculation that we mentioned in that section. 12.3 focus on calculation of partial derivative. 12.4 will combine all the partial derivative for a single function to create a thing that's called a total differential. Total differential is very useful for approximation. What other purposes? And also, total differential's coefficient will be the gradient. And next section in 12.6, we talk about gradient, which is also a term that related to all the partial derivatives together. 12.2 is multivariable chain rule. It's useful for finding derivative when you have a compositional function in your multivariable function. 12.6 is directional derivative. Yesterday we practiced directional derivative, so probably going to skip that today. 12.7 is calculation of tangent line, normal line, and tangent plane of a surface. So that one was focused on surface. We did mention surface in chapter 10 and So now we're coming back to the idea of having a surface represented by v fxy. 12.8 is calculation of maximum or minimum value of a multivariable function. So there, it's often a multivariable function with a constraint. 12.9 is a new method for calculating maximum that's called Lagrange multiply method. So most of the popular topic we have some question on the final exam practice set. So try to practice what work assignment so you know what question you're supposed to practice more. All right, this is a partial derivative calculation. Let me find out if I had that. We'll practice the multivariable partial derivative calculation. Let's try this question. It is again one of the questions that we have what word. So let's try. It's not overly difficult, but you do have to remember how to apply quotient. Or you can make a negative power and apply power. So product rule and power rule combined will probably replace quotient rule. But find the df/dx. There's two partial derivatives to it, so we find the first one. So it's not a overly difficult question because it's a conceptual. It doesn't involve number. It's all variables. You should sit down and try to look at the calculation. Right, so here are the function. Maybe it's too small. Let me copy it a bit. So that was a function. We're trying to calculate this partial derivative. Okay. So according to the differentiation, the structure is a division. So we would have to remember the quotient rule. We get a high over low. According to quotient rule, the quotient is the denominator squared. The numerator is low b high minus high b low. I guess that's how people memorize it. Let me try it. So we differentiate the numerator first. So basically we'll find the derivative of the numerator and multiply by the denominator. Minus this time we're going to find the derivative of the denominator, multiply by the numerator. Or you can switch the order and just write h times l. Kind of alternating when we are trying to differentiate. So this is our division. So whenever you find derivative division, which is this case, you will always square the denominator. Yes, I should. This is equal to the denominator have to be squared. Okay, I didn't write it wrong. Okay, denominator should be square and the numerator take time. You'll find derivative of the numerator. So we will find it's dx, right? B dx of the numerator, which is this part, the h prime. Numerator is 8x plus 3y. Right, you want to multiply the denominator. Denominator is negative 7x minus 2y. Minus that was this minus. So we minus the numerator stay the same, which is 8x plus 3y. We'll differentiate the denominator with respect to the x. The denominator is this. If you differentiate with respect to the x variable, it's negative 7. So we will multiply this by negative 7. Now, one of the things, this part, the differentiation, if you differentiate with respect to the x, it's actually 8. Okay. So to start the denominator will be the same. There's really no change to the denominator. All the action, all the calculation are the numerator part. The numerator will be 8 times negative 7x minus 2y. And then there's negative 7, there's negative 7, it's really positive 7. So plus 7 times 8x 3y. And then you would distribute those coefficients and combine lectures. The rest is trying to figure out what was going on in the numerator and simplify it. And that would be one of those cases. I hope that you were able to finish your calculation. Andrea, I think your answer is no. Let's see. Yeah, it was not that one. We can go back to the calculation. And there was like, I was debating between two of them. So you see, we will have 8 times this and time this. We have 7 times this and then time this, and we combine the coefficient. So it should be. That's right. Thank you. So double check your calculation and to finish the numerator, it will look like this. There's no change to the denominator. As you can see, all 4 choices have exactly the same denominator. It was a numerator that has some algebra that we have to do. Okay, it's negative 56x. Should type. What's your answer?
Oh, wait, what?
What was the choice?
Oh, I see now. I just mistook, I was stuck between which one was the positive.
That's right.
I was stuck which one was 5y.
Yeah, so let me try to type it out, it's easier. Whenever I try to write it like with my own word, I was not saying the right number. What is this? So numerator should be negative 56x. Negative 56x minus 16y. And then positive 56x, positive 21y. That's after we distribute the coefficient and realize the negative 56x will cancel the positive 56x. So numerator really is 5y. Right, 21y minus 16y, 5y is numerator. And then again, there's no change to the temperature. So negative 7x minus 2y squared. All right, if we zoom out to see the whole calculation, that's the entire calculation of this. It's a functional equation. There's not a lot of detail except some algebra in the numerator when we try to combine like terms. The final answer should be If you haven't really submitted, I turn on the scanner again. Sorry that earlier I have to turn it on to find out who answered what. Are you able to push? Anyone else? No. Oh, show what we have so far. Let me see. Where? Are you online? The answer is, okay, yeah. So the answer is A. So now everybody's answer is A now. Let's move on. So that was one of the exercises for chapter 12. I didn't single out every section's question for practice for today. We'll see if we have the extra time. And I just want to try to go through every content and list out what we were doing the whole semester. All right, chapter 13 is multivariable integration. So chapter 13 is kind of different from the rest of the section. We're not looking for object, and there's no line or equation of plane. So we're really moving on to a prediction of integration. But we're not doing, we've done a lot of integration in calculus 2, if you remember. Calculus 2 work on chapter 5, which is basic integration idea, integration concept. Chapter 6 is integration method, and then chapter 7 was application of integration. And then we have more integration in chapter 8. In chapter 9, we're working on parametric equation. So pretty much the whole calculus 2 heavily focuses on integration. But now this chapter is multivariable integration. So if we're a little bit forgetful with our integration formula, you may find many of the sometimes you may find the integration a little awkward, a little difficult to do. Now, 13.1 is integrated integral. So it's kind of bring out the idea of when you do a double integral, you have to finish the integration in the inside first, and then you can do the second layer of the integration. So that's 13.1. The reason the integrated integration is very important is because the order of operation affected the integration result. 13.2 is volume calculation using double integral. So that's assuming your surface is represented by z equal to fxy. So the z equal to sy, which is your integration function, presented as a boundary of your top and bottom of your z value. Therefore, we only have to integrate the x, y with the other two dimensions. So the vertical dimensions already in the integration function. That's why the three-dimensional measure can be calculated using a two-dimensional integration. Now, 13.3 is polar coordinate in double integral. That is whenever the integration region is circular, then it's difficult to use rectangular integration variable. So then one of the key idea is in polar coordinate for integration, you have to do the change of variable. It's from variable xy onto the variable r and theta. Your integration have to change the integration differential dA has to change to r dr d theta. There's actual r that's going on. Occasionally, we might forget to multiply the r. 13.3. 13.4 is a physical idea, center of mass. This chapter focuses on center of mass calculation in the two dimension. So the center of mass will have an x value and y value. In chapter 14, we have, well, in actually section 13.6, we have a triple integral. In there, we do have center of mass calculation. That was for three-dimensional solid. So the center of mass will be a three-dimensional coordinate, x, y, z calculation. 13.5 is surface area calculation. This is surface area calculation that is square root of 1 plus partial derivative x squared plus partial derivative y squared. That was a surface area calculation. It was kind of similar to what we're doing, the calculation of length of the curve, because the root is a formula rooted from an extension of the second theorem. A surface integral also is a special surface integration that's related to 14.4. So now we have the whole book finished. Many of the concepts are connected. And 13.6 is triple integral. So now it's three-dimensional integration instead of double integral. So your triple integral can be applied for calculation of the volume and also can be applied for calculation of the center of mass. 13.7 is a change of variable from triple integration. Instead of doing the regular x, y, z, you can also use spherical coordinate or cylindrical coordinate. That's whenever the integration region is in a circular or cylindrical format, then we will do spherical coordinates. That's sometimes lower or ease the level of difficulty, lower the level of difficulty. Integration. That's chapter 13. I don't remember see or identifying any question for practice, but we'll see any question we've done in that chapter. Right, for chapter 14, we've done that recently, so you probably still remember. These are the six sections in this chapter. We started out introducing vector field, and then with vector field in this relation with a line, we have line integral. In a vector field relation with the surface, we have the surface integral. So if you're doing a line integral, then the integration function will change according to the line, the equation of the line. If you're doing a surface integral, then your integration function or the vector field will change according to the surface equation. The Green theorem is a way to write the line integral into a double integral. The divergence theorem is a way to write the surface integral into a triple integral. And Stokes theorem is really an extension of the Green theorem. So in a way that section 2, 3, 6 are connected, and section 4, 5 are connected, and section 4 is also connected to 13.5. In a way, there is some sort of subtle connection between all the sections we learned. All right, this is a practice question. Okay, I actually should remember that was a solution. Okay, this is a question, actually accidentally. That was a question I was gonna ask us to practice. Okay, so it's a surface integral calculation, and the vector field is given in the vector form. It's in relation to the surface of a cube. And that was similar to some of the question that we have on web work. So the three-dimensional region is inside a cube, which is 2 by 2 by 2. So it's a three-dimensional cube with a length of 2. Okay, so let's try. So then it's nice that it's in the cube. That way, the integration region will definitely be a three-dimensional. So you'll be having dx, x is from -1 to 1, dy, the y is from -1 to 1, and dz, the z is from 0 to 2. But first, you have to identify the integration bounds, the integration limit. So let's see. We definitely had some similar question on web work, but this is the one I already had. So remember, surface integral was something we studied in 14.4, but in 14.5 we had the divergence theorem. Apply divergence theorem, a surface integral can be converted into a triple integral. So this is essentially going to be a triple integration. So you apply the divergence theorem, and you need to know how to calculate divergence. If there's anything special about any vector field that we need to know how to calculate divergence, we also need to know how to calculate the kernel of the vector. This one was about divergence. Let me turn on the timer. So let's see. Many of us say. Thank you. Let's try to review the divergence theorem. It is basically a way to convert a surface integral into triple integration. This is a surface. The surface is a boundary for a three-dimensional region. Yeah, so the surface actually is closed. The surface has a closed, that's the boundary of certain three-dimensional region. And so, okay, so I'll just write you F as the vector field. S, which is equal to a triple integration of divergence of the vector field dV. That's the divergence theorem. So to be able to calculate or apply divergence theorem, we have to be able to calculate the divergence of the vector. In this case, we have a vector that's divergence of vector is not a vector. Divergence of a vector is a function. It's a single value function. So we find the derivative of the first component with respect to x, which actually gives us 0. Because y squared z is the first component, it doesn't have x. So you differentiate with respect to x, you'll be equal to 0. The second component is a y component. We differentiate with respect to y, we'll get 3y squared. Oops, not that. 3y squared. And the last component we differentiate with respect to z. Derivative of z equal 1. So x times 1, which is x. So that's what we're gonna triple integral. So the triple integration applying divergence theorem, you're gonna have triple integral of 3y squared plus x. Now you look at all the integration region. I would prefer to integrate e to dx, which means x is from -1 to 1, and then dy, and then y from -1 to 1, and then dz, and v from 0 to 2. I guess the integration order does not matter. We don't have any transcendental functions. It's pretty much in the calorie for integration. That's the integration part. It's the calculation part. Once you reach this part, I guess you could finish the calculation. I'm not sure how many of you already have the answer. Thank you. If you don't have the answer yet, let me go back to the calculation. So let's say I would start with calculation of the inner integral. That's this part. With relation to the x and derivative for the 3y squared. We'll multiply by x plus the antiderivative for x. Dx is x squared over 2. So we find the antiderivative, we will have evaluation at x equal to 1. And because of the x, right, x equal to -1. So you see, if you evaluate this when x equal to 1 or -1, the x squared would all equal to 1, and so it's going to be 1/2 minus 1/2, which cancel itself. The only thing you see a value would be 3y squared times 1 minus 3y squared times -1, which equal to 2, right? 2 times 3y squared. So this is going to give us 6y squared. We have 6y squared dy, and then we're going to work on the second layer of integration, dy -y. Maybe I should use the same color since I've been trying to track what we are doing. So sometimes I get lost in the process. Do I do a middle integrate, a lot auto integrate? Where was I with integration? So definitely try to find a way to be in control of which step are we on. So antiderivative of this will be 3 right, 6 times y cubed over 3. The 3 will cancel with 6, which is 2. So it should be 2y cubed. That's antiderivative. And I'm going to evaluate at y1 y equal to -1. When y equal to 1, you have 2 times 1, that is 2. When y equal to -1 is -2, 2 minus -2, that gives us 4. So then finally, since the integration is 4, you'll have 0 to 2 for the z. And then integration of that, you know what it is. Right, so I pretty much finished the majority of the calculation steps. It's pretty much all the calculation involved in this. It's clear enough.
Okay. Yes, I gotta sleep.
I kind of try to zoom out to see. So this is, for example, applying the divergence theorem. Let me know what was your answer. Right, you don't have your answer yet?
Oh, I'm currently working on mine, so. Oh.
That was a calculation, that was the answer, but you're gonna calculate it.
Oh.
Go back with the answer. Okay. All right, I think we finished with this question. I hope that you're, if you haven't calculated, maybe I should show you the calculation. This is equal to, bring the 4 outside, or the antiderivative basically is 4z, right? 4z has derivative 4, and I'm gonna evaluate it as equal to 2, and then calculate it as equal to 0, which would be 0. So 4 times 2 is our final answer, which is 8. So answer 2. Finish this, and then the outside will be bz, right? It went up all the way down and then back over here. Hope it's clear as far as the process. So the final answer should be 8. Okay, guys, let's see. Okay, so that's the answer that we had so far. Any questions? I hope I didn't make it extra difficult for you to follow through. Nice. The scanner's still on. If you haven't submitted, you should be able to submit now. I don't know how many of you are still with me, but that was it for this question. Question number. The question about applying divergence theorem to find out the calculation value for surface integral. All right, here are a more organized solution. I was telling you guys I was accidentally brought back to that page. The process will be, now that we have the vector, the vector field, we'll find the divergence of that vector field, which is differentiating every component according to the position. ddx of the first component, ddy of the second component, ddz of the last component, added all together. That's the definition of divergence. According to divergence theorem, we'll be able to calculate the surface integral using a triple integration of the divergence. So we will integrate based on the integration order, and then that will be the final answer, answer state. And that's pretty much what I had in mind today. And we have a few, we'll be 15 minutes, at least 15 minutes left. So let's practice a few more questions. Went over a lot of questions for chapter 10. Some of the question on chapter 14, maybe I should try the question from 13 to 12. We've done that question. All right, this is a question that we have done in the past as well. I don't know if you still remember. That's the absolute maximum and minimum of the function of a triangular region as decided in place. Okay. So because it's a triangular region, so it actually have a couple of consideration. We've done this in 12.8. I don't know how comfortable you are going like calculating this kind of question. Because of the triangular region, we have to identify the max and min value of this function inside the triangle, and also max and min of this function on the edge of this region. And also, when you are considering these edges, the edges are an equation of a line. And obviously, we're not considering this function's max and min on the entire line. It has to be on part of the line. So we have to have a pretty good idea about where is the max and min of the x value, where is the max and min of the y value. For example, on the line x equal to 0, x is equal to 0. What about y? I mean, x equal to 0 is a y-axis. On the y-axis, do we go from the whole y value? Do we go y start from where ended from where? So I definitely recommend drawing out this and try it. I think we did it together in class. Now that we're at the end of the semester, I wonder how many of us can find out the maximum independently. It's one of those questions from 12.8. So obviously, we have to find a critical point of the function. Critical value of critical point of the function is when the partial derivative equal to 0. So setting a partial derivative equal to 0 and see if that provide a number that is the minimum or maximum. So find minimum, maximum inside the triangle, minimum, maximum on the edge of the triangle, and then with everything considered, the highest value and the minimum value are the absolute maximum in the entire region. Give you some time and then we can work on these together. You might have notes, you might have some notes from the past that we did it together. Thank you. Right, let me try to start it. We'll look at what was inside, what was on each of the edge of the triangle. Let's try to look at what happened at every scenario. All right, first we need to know exactly what was this region. It's in the XY plane. All right, so what we're calling x equal to 0. If x value equal to 0, that's essentially the y-axis. That's x equal to 0. Now, if the y equal to 0, if y equal to 0, that means the y value equal to 0. That's essentially the x-axis. All right, and then the last one was the x plus y equal to 2. It's a line that intersect the when x equal to 0, y equal to 2. If y equal to 0, x equal to 2. So that's basically 2, 0, 0, 2. It's a line that crosses this one. So the triangle that we're talking about is right at the edge. We have the highest y value is 2, highest x value is 2, lowest value at 0. So that we know y is between 0 and 2, x is between 0 and 2. So what we're gonna do is, if you only look at this function, discard the range. Make it easy to type this. Right, so when we just look at the function definition, f is equal to, just be large enough, x equal to x squared plus y squared plus xy minus 3x plus 3y. So this function discard the boundary. Then what we're looking at is a unconstrained max and min. In order, well, this is pretty much considered the inside of the triangle. Then we're going to look at the edge. So we have the partial derivative in x, which is 2x. We're trying to find the critical point now. 2x plus y and then minus 3. That's this derivative. You find this derivative with respect to the x equal to derivative x equal to 1. 1 is y, and that one has negative 3. So that's this we set equal to 0 in the effort of trying to find the critical point. This partial derivative in y, you have 2y, and then another y term is plus x, and then plus 3, which equals 0. So we have this, we're setting this, we're setting them equal. So we have this system equation. We'll be able to find the critical point. We're just going to find a critical point, right? Find the critical point. It's the same definition in part 1. To find a critical point, we set all the partial derivative equal to 0. Just to find in general, if the function have x, max, and min, disregard the triangle. This is trying to find the maximum inside the triangle. So then we have to solve the system equation. It's degree 1. We can definitely turn that into a matrix and solve the inverse matrix for the 0. But not only the linear method will be find a substitution method. From the first equation, you can see that y is equal to negative 2x and moving the x over plus 3. Negative 2x plus 3. And then you can bring that to the equation number 2. I guess you can write it this way. You bring this result, well, it looks like a negative sign. Right, from the second equation, we have that 2y and 2 times y equal to negative 2x plus 3, and then plus x, and then plus 3 equal to 0. So we can kind of combine these two equations in order to find the critical point. Then we have negative 4x plus 6 plus x plus 3 equal to 0. Okay, that will be negative 3x plus 9 equal to 0. Not mistaken. So we should end up having that 3x equals 9. So x equals 3. And that's way out of the triangle. So even if this function have a critical point, it's not inside the triangle. So we will be able to find that maximum minimum value at that point. Let's see if I made any calculation error. Y equal to negative 2x plus 3. So negative 2 times 3 is negative 6 plus 3. The y equal to negative 3. And then see if it satisfies both of these equations. So our critical point happened as 3, negative 3, which is not inside the triangle. So that also indicated our maximum should happen somewhere along the edges. Andrea, did you finish the calculation for the critical point? Well, I said what was your critical point? Huh? You haven't found the critical point. So what was your method then? Yeah. Huh?
I didn't do
Oh, okay. Anyway, so this is really what we're gonna do right now to find a critical point and find the maximum is to determine what happened inside the triangle. But turns out the critical point is not in the triangle. So we find a point that was unit would be 3, negative 3, because the critical point is not at the inside the triangle. So we now gonna focus on the edges. Right, so number 1, inside the triangle, we have put a point that was 3, negative 3. That will be way over here, 3, negative 3. Based on 12.8, we would try to determine an adequate one. Do we have a max? Do we have a mean? Do we have a saddle point? But since this point is not even inside the triangle, we don't have to do all that. So we will focus on what happened on the outside. So now the inside of the triangle is not working. So we're gonna find out every edge of the triangle, what happened. Do we have a maximum? What was the maximum on those edges? So I just want to make sure you guys are looking at my calculation. Is there any mistake I did? It was okay? Because it surprised me that the 3 and negative 3 is now in the triangle.
I was sorry. I thought you were on a different question. I didn't realize you asked.
Yeah, but
Another question?
this question,
Yes.
do you find the critical point?
Yeah.
Is it the same? I'm just trying to preventing myself going forward.
Yes, I did. Yeah.
It was at that number. Was it this number?
Yeah, it was.
Okay, all right, so I'm just saying that based on the critical point, it won't work with this calculation, no matter whether you put it in, it's a max or mean or settle point, it won't affect our calculation. I see you guys already finished it already. So let me see what you have so far, and then we'll probably work out the edges. This thing is colors. I guess I have it on the whole time. Scanner was on, so ran out of battery. So let me finish while this thing is charging. So we're gonna look at on every edge what happened. Actually, the edge could be slightly easier because we'll turn the two-dimensional function into a one-dimensional case. For example, let's start with x equal to 0. So the same function to start will happen inside. If x equal to 0, that was the edge on the y-axis. So it's talking about what was going on here, right? Between 0 and 2. So that on that edge, x equal to 0. What about y? Y is really in the interval between 0 and 2 as well. So it's really finding the maximum of this function when x equal to 0, when y between 0 and 2. So you have this f function. It will change when x equal to 0. So it become y squared, x already equal to 0, and then plus 3y. So that's what will happen if x equal to 0 and y is actually free. with that, we have the derivative, which is 2y plus 3. And then we have a critical point critical point of this will be y equal to negative. When you said the derivative will be 0, so it's negative 1.5, which is again now in the interval, so the maximum can only happen at 0 or 2. So when y equal to 0, we have f is equal to 0, right? We're trying to find maximum of this function. And then when y equal to 2, that's the other endpoint of the interval. We'll have to look for maximum at the edge of the interval. So all the time. F would equal to 2 squared plus 3 times 2. That is 4 plus 6. That was 10. That's on that edge. And then for y equal to 0, that's another scenario. Then x will be between the interval 0 to 2. And then again, you look at a change your function definition because y is now R0. You have the x squared plus 3x, and x is between 0 and 2. You have derivative, you have to set the derivative equal to 0 to find a critical point. The derivative is 2x with minus 3. 2x minus 3. We have a critical point, which is 1.5. When you have the 2x minus 3 equal to 0, x equal to positive 1.5. So now we have our calculation of the y value, x value, x equal to 0, then f also equal to 0. That seems to be the minimum on this line, on this edge of the triangle, x equal to 1.5, which is one. You find your f equal to 1.5 squared minus 3 times 1.5. This might be a minimum point. And then x equal to 2, where you have f equal to 2 squared minus 3 times 2, which is negative 2. So those are the maximum on this edge, and then we'll find the maximum on the last edge. So it looks like we're out of time. Let me see what we have so far. This is collectively what we have. We have to finish with all 3 edges. I'm guessing the maximum should be on the last edge. It should be on the x plus y 2, and you will put y equal to 2 minus x in the effort trying to. Sorry, this thing was out of power. I should bring more devices. It's really not gonna charge great enough. Anyway, so what do you have your answer? You can see there are 2 answers. Which one is the right one? You finish your calculation? I won't be able to scan. Sorry. This thing is now officially out of power.
Oh,
Okay, you had it on the whole time frame. That's why the cell phones can't take it with the power drains. Yeah,
it's all right.
so what do you think is the right answer? Is it B?
Wait,
Probably. Did you guys actually finish it? No, you did? What was the maximum? What was it on the last edge of the triangle? Where was it?
Yeah, it was on the hypotenuse.
On the hypotenuse of triangle. Okay. That's what I think, because on the first 2 edges, I didn't find it. Anyway, that will be it for today. It's okay for the last question. I probably don't consider that before. But I also know that you guys are here, and now we have a couple questions already, so there's no problem. Thank you. That's it for today. Thanks. We know that power can go out.
You take it on 12. Yes.